Okay, our final presenter today is Dr. Seokjhin Kim from Oklahoma State University, and he'll also be talking about some of his work of him and his team on membranes, but his membranes are focused more on oil-water separation. So, Dr. Kim, I will turn it over to you.
Thank you. Thank you, Dr. Wagner, for introduction. Can you see the screen? Okay, 1 second.
Oh, yeah, that looks good right there.
Oh, okay, great, great. Thank you again. So today, I would like to talk about the hydrophilicity-controlled inorganic membranes for oil and water separation. So today we have produced water in Oklahoma, and we have approximately 120 million cubic meter of produced water annually generated, and majority of them is disposed by deep well injection, which sometimes makes earthquake. So simple distillation of produced water is feasible, or the injection or trucking, that is expensive, energy intensive. So, and there is cost. So in order to reduce the injection volumes and earthquake concerns, an alternative management of produced water is needed. Treatment of produced water typically requires a series of pre-treatment and post-treatment, including flocculation, settling, backwashing, and chemical treatment to remove target contaminants. Membrane separation is desirable for wastewater treatment process because there is no need for chemical additives, no need for thermal energy, and there is no phase change. In order to remove hydrocarbons from produced water, chemical demulsifiers are needed to remove the surface active agent from oil-water interface. Chemical demulsifiers must match with specific chemical profile of produced water. There are a few predictable model for choosing appropriate demulsifiers. So the process relies on inefficient trial and error serial testing. Also, chemical treatment generating sludge, which can purge pollution. Ultrafiltration membrane have a pore size ranging from 0.01 to 0.1 micron. These membranes are commonly used to separate water from oil and water emulsions by size sieving. The membrane pore size and thickness can be controlled by selecting appropriate materials. For example, there are reports about membranes for oil-water separation, such as polydopamine-coated polypropylene membrane and PVDF membrane to control pore size around 0.2 micron. However, there are two problems. Number one, fabrication. Membrane fabrication process takes extensive time due to control of temperature, pressure, cross-linking. Second, fouling. Fouling decreases membrane flux because contaminant can block membrane pores. Fouling can also damage membrane by foulant, and then there is need to use chemicals for cleaning. So it also can damage membranes. So membranes eventually need to be replaced around every 5 to 7 years. Therefore, there is need to have thermally, chemically, mechanically stable membranes. So starting point in our group was using the zeolite mesh membrane. So what we did was we used stainless steel cell, and then for the oil water separation, we synthesized hydrophilic MFI zeolite membrane on the mesh. So we can see SEM images on the right-hand side. So membrane was designed to make water permeable across the mesh and rejecting oil simultaneously. Water flux was more than 90,000 liter per meter square per hour, and oil rejection rate was more than 99% during 15 times recycling test. For filtering 50-50 mixture of hexane and water. In this video, 50-50 mixture of hexane and water is there. The hexane is oil, which is red. On the bottom, we have water. Then we placed zeolite coated mesh here, and then we simply poured this mixture on top of zeolite mesh. So let me play this. As you can see, this is gravity driven. Driving force was gravity only. And then in a few seconds, we have successful separation of hexane and water mixture. So this is promising part of ceramic membrane or inorganic membrane. However, there is problem. The produced water is more like homogenized mixture, like emulsion. So when we use homogenized produced water solution into this zeolite membrane, it doesn't work. So what we did was we did literature review for ceramic membranes for oil in water emulsion separation. So the scientists generally synthesized ceramic materials coated on the porous support of the substrate like alumina disc, alumina tube, or hollow fiber substrate. In some cases, materials are synthesized on the surface or pore channels of the support to enhance transport efficiency and separation selectivity. For example, the ceramic alumina membrane was synthesized by coating TiO2, nano TiO2 composite onto the hollow fiber or alumina substrate to make membrane hydrophilic. And then more water molecules can pass through the membrane while rejecting oil. So it increases membrane flux. Another example is carbon nanotubes were used and synthesized in the channels of yttria stabilized zirconia support to remove the tiny oil droplets from oil-water mixture. And then rejection was 100%. So we found that ideal membranes for produced water separation require high flux, high selectivity, and long-term stability in harsh conditions. Silica nanoparticles. Silica is an oxide, and it is compound of minerals and synthetic products such as fused quartz, fumed silica, silica gel, and aerogels. Silica nanoparticles size around 16 nanometer belong to super hydrophilic materials. Studies have shown silica incorporated membrane improved hydrophilicity, and also it improved collision resistance of the membrane. So in this study, hydrophilic silica nanoparticles were used and incorporated into membrane to change the hydrophilicity of the membrane. The motivation is to separate water from stable oil and water emulsion by using inorganic microfiltration membrane to increase membrane hydrophilicity to obtain high water flux and high oil rejection rate. So we optimized conditions for membrane separation, such as concentration of silica nanoparticle solution and operating pressures and operating temperatures. This is what we did for the preparation of inorganic microfiltration membranes. Alumina tubular membrane was purchased and clean dried. Alumina tubular membrane was then immersed into silicon nanoparticle containing solution at different concentration of 0, 0.05, 0.5 to 5 weight%. Then silicon nanoparticles was uniformly incorporated onto membrane surface by using ultrasonication for around 15 minutes. Then membranes were taken out and calcined at high temperature of 350 degrees C to integrate silica nanoparticles firmly on membrane surface. So as you can see on right-hand side SM images, on the bottom left, bottom right, after calcination, it was found that silica film remained on the membrane surface. Then we prepared oil in water emulsion with collaboration with Dr. Clint H.L. To prepare oil in water emulsion, cyclohexane was used as this first oil phase. DI water was used for continuous aqueous phase. Water-soluble anionic sodium dodecyl sulfate, SDS, was used as a surfactant. Initially, SDS was added to water and shaken by using a homogenizer for complete mixing. The dispersed oil phase was added in a dropwise manner to make homogeneous distribution. So as you can see, the optical microscope showing the image of feed water is like milky water to measure oil droplet size of cyclohexane in water emulsions. So droplet size was around 2.5 micron, which was larger than membrane pore size of 0.2 micron. So basically, this oil in water emulsion consisted of 500 ppm of cyclohexane and 0.13 weight% of SDS. And then we tested a bottle test, and then we found that there is no phase separation of emulsion at invested temperatures. So this milky emulsion was stable. So this is the experimental setup in the lab in order to investigate separation capability of the prepared membranes. Membrane was installed into a stainless steel cell, and it was sealed by epoxy resin. And then we checked that this is watertight. So this is like dead-end system. And then in the middle, we have 300 milliliter of emulsion added into sample cylinder. On the left-hand side, a compressed argon gas cylinder was prepared to apply a pressure of around 3 bar on top of the membrane feed side. So the separation happens like water permeate across the membrane, and then we have a tank below to gather the permeate solution. So driving force for this separation is pressure. Separation efficiency and permeation flux was defined according to below equations. After getting permeate solution, in order to measure the oil concentration in it, the cyclohexane was extracted from the permeate solution using chloroform. And then GCMS was used to measure cyclohexane concentration in the permeate solution. For this technique, the automatic liquid sampler with injection volume of 1 microliter was used for injection for all the samples. So these are results. The membrane, the figures show morphology of membrane after silicon nanoparticle incorporation. So on the top, there is M0 membrane. M0 membrane means pristine aluminum membrane. There is no silicon nanoparticles. In the middle, we have M.5. It has a silicon nanoparticle. Aluminum membrane was treated with 0.5 weight % solution of silicon nanoparticle. And then along these SEM images, the silicon nanoparticles were incorporated onto membrane surface. And if we see the 2 micron magnification, there is silicon nanoparticle incorporation the uniformly distributed on the membrane surface. However, there is minimal blockage of membrane pore channels. Minimal blockage is found also 20 micron SEM images as well. However, below we have M5 membrane. The membrane was treated in 5 weight % solution. So M5 has more silicon nanoparticle in it. There is still continuous layer of silicon nanoparticles was found or formed on the membrane surface in 5 micron, the magnification image. In 2 micron magnification image, there is aggregation of silicon nanoparticles. Silicon nanoparticles are too much. They are aggregated into membrane pore channels, which narrowed membrane pores. Same thing on the right-hand side. Silica film, partially the narrowing pore channels. So before doing membrane testing, we measured the contact angle of the membrane. So oil contact angle were measured to investigate the wettability, hydrophilicity of the membrane at room temperature and atmospheric pressure. Silicon nanoparticle increased the contact angle between oil droplet and membrane surface, indicating silicon nanoparticle increased the hydrophilicity of the membrane. From M0 to M5, oil contact angle increased around 155 to 165. These SEM images showing morphology of membranes of M0, M.5, M5 before and after separation. Overall, there is minimal morphological change on the membrane surfaces, indicating silicon nanoparticles firmly attached to membrane surface. Below, we have table showing membranes and atomic percentage of silicon. In M0, pristine alumina membrane, there is no silicon. As expected, the silicon was found in M0 membrane before and after separation. M.5 membrane, it was found that before separation, silicon content is around 0.6%. After separation, silicon content decreased 0.45%, which means that silicon slightly reduced, but still majority of silicon nanoparticles remained on the membrane during and after oil-water separation. However, M5 membrane has more silicon nanoparticle incorporation. There is a huge reduction. Before separation, 16.6%. After separation, 7.9%. Which means the M5 membrane silicon nanoparticle aggregated due to higher concentration of silicon nanoparticle, which decrease interaction between silicon nanoparticle and alumina membrane surface. So the larger the aggregate on the membrane, the easier to wash away silicon nanoparticles during separation test. So comparing M.5 and 5, M.5 was better in terms of aggregation. So in order to further estimate the membrane stability, we take care of the membrane permeate solution through M.5. And then we centrifuge the permeate solution at high speed. After that, it was found no observable particles found at the bottom of centrifuge tube, indicating that M.5 is the best membrane for this, and it was selected for further separation. These figures show microscope of feed solution on the left and permeate solution on the right. So it can be found the milky, the emulsion solution, after the permeation test, it changed very clean after treatment. So on the right-hand side, no droplets were found or observed in the permeate. So this operation was by M.5 at 3 bar at 20 degrees C. So this image is still indicating the separation of cyclohexane droplets from oil in water emulsions successfully. Next, we investigated the effect of silicon nanoparticle concentration on membrane flux. On this plot, showing the membrane, the effect of silicon nanoparticle concentration on membrane flux as a function of time. Over time, as expected, there is flux reduction due to fouling. That is inevitable. Membrane modified with silicon nanoparticles showed higher membrane flux than pristine alumina membrane, which is M0. So M0 shows lowest flux, silicon nanoparticle incorporated membrane showing higher flux overall. This is because silicon nanoparticle enhanced membrane hydrophilicity by hydroxyl group on silicon nanoparticle surface, which strongly absorbed the water. Therefore, the membrane allowed more water molecules to be observed on the membrane and then passed through the membrane, which is consistent with the literatures. In the table, there are membranes, oil concentration in the feed, in the permeate solution, oil rejection rate, and the flux. When we compare membrane M.5, when we compare M.05 and membrane 0.5, the flux was similar, around 760, 780. However, when we compare the oil rejection rate, M.5 membrane showing higher oil rejection rate, indicating the effect of silica nanoparticle on rejecting oils. Then, when comparing M.5 and M5, although more silicon nanoparticles provide the higher hydrophilicity on M5, the flux of M5 is around 670, which is lower than 780 of M.5. Again, it shows that the membrane channel might be narrowed due to aggregation of silica nanoparticle on M5. So it was found that M.5 exhibited higher flux and higher oil rejection rate, and therefore we thought it can be selected for further experiments. Second test we have shown was we investigated the feed pressure, effect of feed pressure on membrane M.5. Figures show the effect of pressure on membrane flux as a function of time. Also, continuously, it's showing the flux reduction due to fouling. Flux increased with increasing transmembrane pressure from 29 to 58 psia. So driving force increased the feed side, so membrane flux increased by more than 1,000 liter per meter square per hour at room temperature. Third, we investigated the effect of the temperature, and then the figures show the membrane flux over time again. The literature studies show the flux increase with increasing temperature while maintaining oil rejection rate. So similar to literature, flux on the our work increased with increasing feed temperature from 20 to 60 degrees C. Flux gradually increased. And then comparing temperature from 20 to 60 on the table below, oil rejection rate was stable around 92, 94%. However, there is flux enhancement, so which shows that the temperature affected flux, but temperature did not affect so much on oil rejection rate. So now the future work for this will be cross-flow system, as the Christine previous presenter showed this work. Our lab set up the cross-flow system. The previous data in my presentation was from dead-end system. So dead-end system is, as explained by Christine, the flow is perpendicular to membrane surface. However, the advantage of cross-flow system, the flow is parallel to membrane surface, which can generate turbulent flow between interface of solution and the membrane, which generate turbulent flow, which will decrease fouling on top of the membrane. And basically, we have feed tank on the bottom, and then we have a circulation of water, which is different point. Dead-end system, there is no circulation of water. Cross-flow system, we have circulation of water. So water introduced from tank to the membrane surface, and then the separation happens. The permeate solution across the membrane going to the collection tank, rejected flow going back to the tank. And then everything is under control. Pressure and temperature is control over. So which means it can provide more stable, reproducible, and less fouling system on the membrane. For example, if we use the same membrane M.5, can compare between dead-end system and closed flow system. And it can provide also long-term operation as well. So by far, we operated more than 1 day, but with the students, Diako Mahmoudi, we will continue this work. In conclusion, in short, we demonstrated the method to incorporate silica nanoparticle into alumina membrane. It successfully separate the oil and water emulsions with highest flux, more than 1,000 LMH, more than 94% of oil rejection rate. So this research was performed by graduate students and undergraduate students in my group. And thank you for your attention, and thank you for your time.
Great presentation, Dr. Kim. We've got a couple of minutes left for questions. If anyone has questions for Seokjhin.
I have a question. My name is Babu Fatipure. You can hear me?
Yes, yes.
Kim, Dr. Kim, interesting talk. I really liked it. Very nice. I have a simple question. Why did you choose cyclohexane for this work? Question one. Question two, I'm just wondering how 60-degree, I know the flux increased, but that may also lead to volatilization of volatile compounds in produced water, and also some solubility increase in oil. So those are the simple two questions, but I like the work. Really nice. If you can help me understand it, great. Thank you.
Thank you for great questions. First question, that's a good question. Firstly, we started with hexane, and then we changed it to cyclohexane. Simply, there is no big reason. We thought hexane is like linear, and cyclohexane is like more rounded. Then we would like to try what will happen for cyclohexane as an oil phase. There was no big reason to choose cyclohexane.
A couple of things I want to add to that. Cyclohexane is pretty easy to degrade in the environment. Microbes love it. Eat that for breakfast. Okay, so 100 ppm looks pretty high concentration. I'm just throwing some questions so that we can have a little discussion.
Right. Yeah, thanks for the information. Yeah, I didn't know about that, and then yeah, that's good information. And the second question to the temperature effect. Yeah, I didn't think about that aspect. Yeah, definitely the solubility of cyclohexane will change into the feed solution, definitely. I suppose in our experiment, there is no significant change in oil rejection rate, but there is some driving force increased due to the temperature, the higher the molecular transfer, and then we got the higher flux. Yeah, so the cyclohexane, the solubility and that effect, I'm not so sure at this point, but in the future I need to consider that aspect.
Yeah,
yes.
But 60-degree will definitely result in little volatilization loss. Second is 60-degree operation will be very expensive in real world because you have to heat.
Right. Definitely. Yeah.
Thank you.
Yeah. Thank you for the questions.